Hello, everybody. So we are going to continue our discussion of improper integrals. So last time we looked at one similar to the graph I'm seeing here, and this expression here, where I have the function x to the negative 1/2 power, and trying to integrate that over from 1 to infinity, right? This infinite area, and we saw in some cases we can make sense of that. This one, however, doesn't, right? You might recall that one of the things we looked at was that if we have an integral of this form, this diverges if p is less than or equal to 1. So in this case, it's less than 1. It's 1/2. So it diverges. So I can write, sometimes we might write infinity here. Let's just be a little more careful, right? When we write that, we just mean it grows without bound. But I'm going to just say this diverges, right? In other words, this green area in the graph, as we keep up adding more and more area, as we move off towards infinity, just keeps getting bigger. It's not going to approach some number, right? However, what about the other side of this thing? There's this little white strip here between 0. Let's change our bounds just a little bit. Let's give ourselves a little more breathing room, right? Between the y-axis and y equals 1, that goes up towards infinity, right? So, well, I can just fill it in on here. So instead of looking at this green in this direction, let's look at this thin strip. So let me change my bounds a little bit to make this easier to see. Something like this. Let's make it even better. Let's go to, right? So now, instead of looking from 1 to infinity, we're looking at something like this, right? Where we have an asymptote for our function, and in the y direction, this area is going off towards infinity, even though the bounds, so what I'm saying in terms of integrals is, let's instead look at the integral from 0 to 1 of x to the negative 1/2 dx, right? So the previous one, the one on top, we were looking to the right of 1. Now I'm looking between 0 and 1. We have a similar sort of problem, though, right? It's an infinite area. This shape is extending upwards with no limit to how high it gets, right? If you want to get a very high value of the function, you just take a very, very close value to 0, a positive value very close to 0, right? We're going to use a very similar idea. Remember what we did to get our infinite integrals before. We had this value t, right? We have some shape, some function. We want to get the integral from some number a to infinity. What we do is we have a value t. We get the integral up to that value t, but then we move t further out with our limit. And then we move t further out with our limit, right? We keep taking larger and larger spans of the area and see if they approach something. So we're going to do a very similar thing here in the other direction. In other words, what I'm imagining is I'm taking these areas, right, between something a little less than 1 and 1, between 1/2 and 1, between something very close to 0 and 1. And as I get closer and closer to 0, do I start approaching a number, or does this area just get larger and larger and larger? So we're going to use a very similar idea here. I'll define it specifically, but just using what we know, what I'm going to say is, or what we're going to do is, we're going to define this other type, this type 2, sometimes some texts refer to it as, in terms of a limit. The limit's going to look a little bit different this time. Instead of t approaching infinity, t is going to be approaching 0 from the positive side, right? And so t right, goes here. Again, what we're imagining is t is the lower bound of our integration in this case, and we're letting t get closer and closer to 0 and seeing if the integrals we compute as it gets closer and closer to 0 become closer and closer to some number. So again, as in the previous video, we deal with the integral first. The limit is its own thing that we'll deal with at the end. We're going to deal with the integral first. So this integral has an antiderivative x to the negative 1/2 has an antiderivative of negative 2x to the 1/2. We're evaluating from t to 1. We get the limit as t goes to 0 from the right, from the positive side, right? We can't approach 0 from the left because these are negative numbers and we're taking a square root. We're only dealing with real numbers. Otherwise, this limit will behave the same. That positive part just makes sure we're putting in positive, from the right ensures we're putting in positive values so that our square root can handle it. All right, so evaluating this, we get negative 2 times 1 to the 1/2 power plus 2t to the 1/2 power. And this looks like the limit as, oh, sorry, there's no negative there. Pardon me, that's an error on my part. I'm confusing the negative there when I take the derivative. Of course, if we have 2x t to the 1/2, we take the 1/2, taking the derivative to check this, there's no negative there. Pardon me. All right, which means that this is still negative. All right. Okay, so we have the limit as t goes to 0 from the positive side. We get 2 times the square root of 1, which is just 2, minus 2t to the 1/2. And what happens to 2t to the 1/2 as t goes to 0? That gets smaller and smaller. This is continuous at 0, at least from the right it is. And so we can simply substitute the value in. And so this limit is 2. Okay? And so this is a very similar idea to the ideas that we used in the previous video about the other type of infinite integrals. There's also a little interesting geometric, maybe geometric way to look at this, just an alternative way to look at this. So this integral, or this function, x to the negative 1/2 from 0 to 1, I can also think of it, so let me do a little sketch over here, from 1 to 0 in the x direction. Looks like this. Right, well, this is exactly the same as the function, so y equals x to the negative 1/2 is equivalent to saying x equals y squared, except we're only looking at the positive, we're only looking at positive values. Right here we could have negative y values. We're only looking at the positive values here. Pause for positive, so we're taking y to be our input. We could integrate this from y equals 1 to infinity. 1 to infinity. 1 over, oh, sorry, there's a negative I'm missing here. So that's 1 over y squared dy. We did this integral in the last video and found that this had a result of 1. Okay, so the only difference was we were using x instead of y, but everything about the integral behaves the same. So what that's saying is this area from 1 to infinity is 1. All we've done with this new integral is added this square right here, and this has an area of 1, and so we get a total area of 2, right? The square here doesn't look like a square because the graph's scales aren't equivalent, but you can see this, there's a square at the bottom from 0 to 1 over to 1, right? That corner there is at 1, 1. So just an interesting little tidbit that it matches with what we did last time in terms of the results. Sometimes this stuff feels a bit like magic, and so maybe it's nice to see at least it's consistent with itself, if not our intuition. Okay, anyways, back to our definition of improper integrals. So last time we had 3 rules for improper integrals going at positive infinity, negative infinity, or both. We're going to call this set of rules type 2. This is not some official name, just to keep it distinct from the last thing we did. And again, we're going to have 3 situations. If f is continuous on the interval including A, excluding B, and discontinuous at B, then the integral from A to B of f of x dx is going to be the limit as t approaches b from below a to t f of x dx if the limit exists. Okay, so the picture is, this is not the one we did. This is a picture where you have a function that has some kind of asymptote to the right, and we want to get the area from A to B, right? And so we imagine getting areas, getting closer, right? Taking t closer and closer to that asymptote, getting more and more strips of that area as we take the limit. All right, and then the one that we just did, if f is continuous on this interval where it's continuous at B but not A, and it's discontinuous at A, so we just did this one where A was 0 and B was 1, then our integral from A to B of f of x dx is going to be the limit as t approaches A from above, t to B, f of x dx, provided the limit exists. Oops, limit exists. All right, so that's the one we just did. And then finally, if f is discontinuous at C, where C is between A and B, and both A to C, f of x dx, and C to B, f of x dx converge, then we'll say, let's go down one more line, the integral from A to B f of x dx is equal to the integral from A to C f of x dx plus the integral from C to B f of x dx. Okay, so there's a whole lot of words and notation there. Let's draw a quick picture of what this one is saying. If we have a function that has an asymptote and we want to integrate across that asymptote. So let's say my function looks something like this. Maybe it does something else on this side. And let's say I have A, this asymptote is at x equals C, and then B is out here. The area we are trying to integrate is all of this area on this side, right? This goes off to infinity there. And we also want all the area on this side of the asymptote. Then the way we get it, this side is the integral from A to C, f of x dx. This side is the integral from C to B, f of x dx. And we add those two together. And when we do that, we get the integral from A to B, f of x dx. Now, both of these have to exist because both of these, from A to C and from C to B, those are the first two bullet points in this list, right? The one from A to C is like the first one where you have an asymptote on the right, and then the one from C to B is one where you have an asymptote on the left. So you have to do each of them separately. If either one of them diverges, right? Same meaning for divergence. If that limit exists, we say it converges. If it doesn't, it diverges. If either one of these diverges, then we say the whole thing does, okay? Right, so if you have a finite area on one side and infinite on the other, in totality, it's infinite. Okay. All right. Let's do one more example. So we did one where we found a converging area, this one of x to the negative 1/2. Let's take a look at one more. Let's take a look at the integral -2 to -1. Sorry, that's not the one I wanted to do. I want to do from 0 to 1. From 0 to 1, e to the x over 1 minus e to the x dx. Right? So notice this function is continuous except at x equals 0, where the denominator is 0, right? These are two continuous functions. When you take the quotient of continuous functions, they're both continuous over their domains, except when the output of the denominator is 0, which in this case happens only when x equals 0, right? That's when e to the x equals 1. So by definition, right, this has a limit. This is defined to be the limit as t goes to 0 from above, just like our last one. 1 to t, e to the x, 1 minus e to the x dx. So now we need to figure out how to take this integral. So there's a lot going on in this. This isn't an obvious integral to take, antiderivative, it's not obvious to me. And then we have to evaluate it, and then we have to take a limit. That's a lot of stuff. I'm gonna do this one thing at a time. I'm gonna first find an antiderivative. Okay. And I will use a u substitution. I'm going to try u is equal to 1 minus e to the x, which means du equals negative e to the x dx, or negative du e to the x dx. This means I can rewrite this as the following, right? Negative du, I put the negative out front, that replaced e to the x dx, u replaces 1 over e to the x, and then this is a simple antiderivative to take. Well, all right, I'll do it in an extra step. Let's just make sure there's no ambiguity, and then we can put back our antiderivative, our substitution. All right, so now I have an antiderivative. I'm going to use that in here. I don't need to go through all that work again. I also am not going to include the plus c because we're evaluating it. So I have the limit as t goes to 0. My antiderivative that I just found is negative natural log of 1 minus e to the x, and we're evaluating it from t to 1. We get the limit as t goes to 0. So when I put in 1, I get negative natural log of the absolute value of 1 minus e to the 1, so that's just e, plus the natural log of 1 minus e to the t. All right, so this first term in here, that's a constant. 1 minus e is a number, it's a negative number, the absolute value is a positive number, a natural log operates on positive numbers, so it spits something out. I don't know what it is, I don't need to know what it is. This is a perfectly good way to write that number. There's no t in here, so the t going to 0 does nothing. Oh, and sorry, I forgot to put my pluses here. Doesn't matter, oh no, it does, well, doesn't matter terribly for this one, but it's still good practice, still correct. All right, sorry. This is a constant, and the limit does nothing to it. So this is the constant, whatever this number is. And we have a limit as t goes to 0 from the right of the natural log of 1 minus e to the t. Well, what happens here? As t gets closer and closer to 0, e to the t gets closer and closer to 1, which means 1 minus something close to 1 gets closer and closer to 1. Sorry, 1 minus something close to 1 gets closer and closer to 0, and as we approach 0, natural log approaches negative infinity. And so it diverges. This limit does not exist. And so we'll say that this diverges. All right. And so this integral does not have a well-defined area, and it seems it diverges there is what we can say. Okay, that is it for this one. I will do some more examples in later one. Thanks, everybody. I will see you next time.